Now we are moving to a very important part of this photoelectric emission, that is the Einstein's equation. Okay, but before discussing Einstein's equation, let us first discuss that is Planck's. First we discuss regarding Planck's quantum theory. Let us first discuss Planck's quantum theory, which was proposed in the year, suggested in the year 1900. Let us discuss first this. Planck's quantum theory. Max Planck was a very famous physicist. He said that the radiations always travel in the form of the photons or quanta or wave packets. Means, he said, Max Planck said, radiations, this is the incident radiation, see, this is the incident radiation which is falling on this metal surface, which I have already described. What happens? This radiation has a form, a particle form. That means it is consisting of small particles which are known as the photons or quanta, and these are the wave packets, means they have got some energy. And the energy of this radiation is given by E is equal to H into nu. E is the energy. Energy of this radiation is given by E is equal to H into nu. This is the energy of the radiation. Where H is, I think all of you know, it is called Planck's constant. And nu is the frequency of incident radiation. Incident radiation. Look, frequency of the incident radiation. This was the explanation given by Max Planck in the year 1900. Okay. And it was, obviously, it can be said, since we have already said that this radiation has the wave nature, for the wave nature of radiation, due to the wave nature of the radiation, or the wave nature of radiation says, what does it say? Nu is equal to C by lambda. All of us know. Frequency is equal to speed by the wavelength. So, it can also be written as E is equal to H into C by lambda. It can also be written. Alright. This is the Planck's quantum theory. From this we are getting these two expressions for the energy of the radiation. For the energy of the radiation we are getting these expressions. Einstein in the year 1905, very famous equation he proposed, he suggested, for which I think you know that he got a Nobel Prize also. Albert Einstein received Nobel Prize due to this famous work, that is Einstein's equation. What he said, let us see that. In normal case, we know that incident radiation is falling on suitable metal. Those metals are called photosensitive metals. You can write down photosensitive metals, like, which are the photosensitive metals? Sodium, potassium, cesium, molybdenum, etc. So, when it is falling on this photosensitive metal, then what happens? Photoelectrons are ejected out. Okay. Then, here, Einstein explained it, why it is happening. Einstein explained this phenomenon in this way. You can say, we have seen this Planck's quantum theory. After that, Einstein said, when it is falling on it, that means this radiation is consisting of the photons. It is consisting of the photons, which are the hypothetical particles actually. These particles are making one-to-one interaction with what? With the electrons of this metal, because you know in the metals electrons are also there on the surface of the metal. Electrons are bound with the restraining forces. These conductors, these are the metals, they are containing a large number of the electrons. Then what happens? One photon, one electron interaction. Okay, due to one photon, one electron interaction. Due to that interaction, I write here. Now, see, first point is when the radiation falls, incident radiation is falling on this photosensitive metal, one photon, one electron interaction takes place. First point. One photon, one electron takes place. Then what will happen? The photon is falling there with a certain energy. How much energy? E is equal to h nu. कितने energy के साथ ये fall करेगा? E is equal to h nu amount of energy. With this energy it is falling, right? And it is knocking out the electron. It should have the sufficient energy. The photon should have the sufficient energy to knock the electron out of the metal. Okay? Then second point. Second point is the electrons are bound, that is the surface electrons. On the metal surface, the electrons are bound with some restraining forces. With some restraining forces. Okay. When these electrons, when these photons fall there, interact with the electron, what happens? They will knock out. But there should be some minimum energy needed to liberate the electron from the metal surface. Means they will be coming out of this restraining force, overcoming these restraining forces, right? So I repeat, the minimum energy required to liberate the electron from the surface of the metal, right? That is called, that much amount of the energy, that minimum amount of the energy is called the work function. Work function is denoted by W naught, and it is equal to, according to Planck's quantum theory, it is W naught equal to H into nu naught. What is this? This is the minimum amount of the energy needed to liberate an electron from the metal surface. हम उसे मेटल सरफेस से लिबरेट कर देते हैं, निकाल देते हैं. उसको निकालने में कितना एनर्जी की जरूरत पड़ेगी? W naught. What is equal to this? Equal to, according to Planck's quantum theory, we have taken the help of the Planck's quantum theory. This is equal to H into nu naught. How much is nu naught? Nu naught is what? Nu naught is the threshold frequency. Okay, it is called threshold frequency. It may be written as Hc by lambda naught. Here, what is lambda naught? Lambda naught is called the threshold or cutoff, okay, wavelength. Threshold frequency क्या है? Minimum frequency below which the photoelectric emission cannot take place, right? And what is cutoff wavelength or threshold wavelength? Just opposite, because inverse relation. Just opposite. That is the maximum wavelength. It is the maximum wavelength above which photoelectric emission can